recall as much as
If you eat a banana like a monkey though, are you a sheeple?
No, you're the monkey.
No, I think you're sheeple because I
Why
don't
would
think it was
you be
I don't think that was a
sheeple?
thing until a guy.
We've clearly proven that it's the better way to prove the banana.
You eat bananas the wrong way, you're from
I
You
just
are
ate so much brain sand.
You do like the peanut butter and then like the raisins on top. You know, like ants on a log.
Oh, yeah.
But usually I get too lazy. I just shove it on my mouth. Set up. My mom doesn't make it for me.
Y'all not like seeing that?
I've seen it on
The
video.
New York,
Yeah.
New York Times is like, oh, here's a cool recipe for the peanut butter and pickle sandwich.
A cool recipe.
Yeah.
Everyone's like, what?
Like, I want to try one more.
Great.
I'll try.
Yeah.
Oh yeah, and be careful if you're talking about food. Be careful with all the eggs that got recalled.
Oh,
What?
Like 203 million eggs.
And lettuce.
And
Yeah,
lettuce.
in one of the states is Florida. So they're recalled. I didn't this morning.
Even if
I thought there'd be like, I was hoping there'd be like no one out at like breakfast because they'd be afraid, but everyone was there still. But yeah, it's evidently like there was like the manufacturer in North Carolina, they do like 203 million a day, like eggs, and then there's salmonella issues, so they were killing all the eggs.
You know the brand was?
I have no idea. Probably all the eggs we buy.
They're from.
Some North Carolina thing. I don't know what the thing is though.
But
Like
it's,
Eggland's best.
it's, yeah.
Is that what it is?
What?
So, but yeah, just to be aware.
It's,
How do you crack it? How about that?
Flat surface, not
You
good.
get two in your hand and then you just.
Wait, really?
Good job, Ryan. Good job.
Wait, on the flat surface?
Yeah, if you do it on like an edge, it like.
You can like crack it like that. If you do it on the thing, it's better. It's much. You can like basically like it's easier to get like chips in it if you crack it against like the side of like the pan
So,
even.
like, goes
But if you just crack it like that like that and then you pull it.
Does it not, like, just come out?
No, I mean it doesn't. At least for me, I don't know. But I'm a bad cook, so don't. Yeah.
Pleasure, good fizzy.
Next review, we'll bring in all these food.
Yeah.
All right. So yeah. So let's.
Oh my gosh, they're sold to Waffle House restaurant.
Oh no.
Oh,
no.
All right. All right. So yeah. So let's go over more hormones and fluid balance, and then we have acid-base one, and then we're gonna do that. So first thing, red blood cell production. So, and this occurs at higher altitudes. So why do we want more red blood cells at higher altitudes? Because of less O2 every breath, right? So we want to have more red blood cells. So even though there's less O2, we can more easily. I forget one out. So now there's more O2 that we actually take into the red blood cells, and then we can hopefully get off into our muscles. So due to hypoxia or ischemia, low O2 in the air, low O2 in the blood, or less blood flow, or less O2, we actually, what can occur there is that in the kidneys, in the heme receptors, now these are located in the peritubular capillary. This is very, very important because these are the ones that make the erythropoietin. These are the cells in the kidney that are going to monitor and realize, oh, there's low O2. So if we have low O2 in our system, the heme receptors in the peritubular capillaries are going to identify this, and they're then going to send, don't worry what the signal is, but they're going to send a signal that is going to cause a different cell type to then make the erythropoietin, and that is the interstitial cells. So interstitial cells of the kidney are the ones that are going to secrete the erythropoietin. Those then go to the bone marrow, and you end up getting those normoblasts that then become the red blood cells. That's what occurs there. Aside from this, what is that molecule that also gets increased at high altitudes? 2,3-DPG. Because keep that in mind. It's like a little side note in case Dr. Yip throws it on the exam. It's like another thing that could be changing for an exam question. Don't worry about what it does, but it helps with the hemoglobin dissociation curve. Yeah. But yeah, so just be aware that's not part of this, but it's something separate. But just keep that in mind as a little side note. So yeah, RAS system. Where the first two exams we were able to get by where they showed us the whole shit and we're like, don't worry about it. Now we have to worry about it. But at this point, hopefully we have a better understanding of it. The first thing, where does renin come from? It's the first part of the RAS pathway. Renin comes from the juxtaglomerular cells. They are a specific type of smooth muscle cells that are part of the JGA. So the juxtaglomerular cells are going to secrete renin. And renin, before we get there, let's show just what causes increased renin secretion. So number one, if my blood pressure is low, there are baroreceptors that are going to monitor low blood pressure. So if I have low blood pressure, what does that mean? Well, my blood pressure is low, right? How do I want to correct that? My BP to go up. How do I do that? Reabsorb sodium, reabsorb water, BP goes up. And that's what renin's doing. It's part of the RAS pathway. So if my BP is low, baroreceptors monitor that, and what are they going to do? They are going to cause an increase in renin secretion. Don't worry exactly how, but basically they're going to cause the JG cells to make renin. That's the first cause, first stimulation. Second one, if your BP goes down, what happens to my GFR? My BP drops a little bit. GFR will go down, but keep in mind, GFR relative to your RPF, that whole thing will stay the same. But initially, right away, your GFR is going to go down. So I have less stuff getting filtered. If I have less stuff filtered, do I have more or less solutes going into my tubular fluid? I have less, right? In this case, it's less chloride, as is the example for the particular purposes. Less chloride means that the macula densa cells in the distal tubule, they're tasting that fluid. And if they sense, oh, there's less chloride here, in not their head, but what they're thinking is, oh wait, there's less stuff getting filtered because my BP is too low. How do I correct that? Increase renin to bring my BP back up. Where have we seen something similar to like this before? In lecture 2. Yeah, lecture 2. Thank you. Lecture 2. Remember what it was? It was the macula densa cells as well in the distal tubule, and they were monitoring sodium levels. And when the sodium levels got too low, what do? They cause changes in the afferent arterioles. That was one of the mechanisms of the autoregulation. You need to know that, and this is the same idea here, but it's to cause a different effect. Macula densa cells do two things. They are, once again, in the distal tubule, they're actually part of the JGA. They're part of the apparatus, along with the juxtaglomerular cells. The macula densa cells, for autoregulation, they taste sodium levels. If sodium's too low, they cause dilation of those afferent arterioles to increase the filtration rate to bring sodium levels back up for autoregulation. For renin production, it's a little different. Instead of tasting sodium levels, they're tasting chloride levels. And if the chloride levels are too low, they're going to send signals to the juxtaglomerular cells and say, yo, we need more renin. And they're going to make more renin to then increase the BP to cause filtration to go up a little bit, to then allow for us to have proper levels for that there. Last one there as well is that when BP goes down, what's the overall response sympathetically? Is an increased sympathetic response, right? And the juxtaglomerular cells receive direct innervations from sympathetic neurons to then cause renin to be secreted. So all three of those stimulants are going to lead to increased renin production to then bring up my blood pressure. So you have to know this now finally. Know angiotensinogen comes from the liver. Know that renin comes from the kidneys, and then know that the aldosterone is coming from the adrenal glands. And in particular, what's happening, renin secreted, goes into the blood. Renin cleaves angiotensinogen to make it angiotensin 1. Angiotensin 1 only becomes angiotensin 2 when I have ACE, the angiotensin converting enzyme. Not the other ACE we talked. There's another ACE for something else, but it's a different thing. I don't remember what it is. But so that ACE here is for the angiotensin converting enzyme. Takes it from 1 to 2. Angiotensin 2 has those 5 or whatever functions it is. One of them being to go to the adrenal gland and make aldosterone. Then that has all of its functions. So that's the whole pathway together. If you don't have ACE, you do not get angiotensin 2. As in, ACE inhibitors are a drug we use because it prevents angiotensin 2. So who would you give ACE inhibitors to? High blood pressure people, as an example, hypertensive people. One of possible drugs you can give. Once again, all these web spider things. Like I said, learn it however you'd like. You don't need to memorize all of this, but you should conceptually, if you understand what we've talked about, all of this would kind of fit into place for you. I found for me, this sort of study is like you tell like a story to a friend. Or like I said, I'm weird, I can study by myself in my room talking like that. So whatever works for you, do that. You can say, oh, my BP goes down, well, renin's going up, and then how does it affect everything else down the pathway? And kind of talk about it from there. But once again, with blood pressure, with renin, RAS pathway, if it goes up, your end result is more blood pressure. Most of this we've already talked about. Angiotensin 2. What does this do? This directly is going to cause vasoconstriction, to bring the BP up. It makes more aldosterone. That's going to help sodium reabsorption. In which part of the tubule? If it's aldosterone? Proximal tubule, right? Proximal tubule. Angiotensin 2 is also going to cause, this is the collecting duct and the distal tubule. Angiotensin 2 also causes sodium reabsorption. That's in the proximal tubule. Also, it's going to cause the FF to go up that we're talking about there because we have that GFR versus RPF thing we already talked about. All of those cause overall what? The sodium is going to get reabsorbed. One thing we haven't mentioned yet that you do need to know for the exam, so I have to make a little note. This goes back to an additional thing that angiotensin 2 does, is that it causes an increase in ADH and thirst. You feel thirsty. Why do you want to do that? What's the end goal of RAS? Increase BP. Because you want to maintain more water. How else can you do that aside from angiotensin 2 and aldosterone? ADH causes more water to get reabsorbed and retained. And on top of that, I want to make sure I put more water into the system as an input. That's what thirst is doing. It's making you drink more, and all those things lead to us to increase our blood pressure that initially dropped. So once again, it's another thing in terms of thirst, ADH. We haven't directly talked about it yet, but RAS pathway can also increase that as well. Okay. So here's the example they're talking about, is that you have a patient, or let me list off all the drugs first, because he puts on the slide, and once again, I had to write all these down. I don't remember any of them. Okay, so he says they treated this patient, he was hypertensive. He had hypertension. Before we look at the cause, we'll go through what they did in terms of what the drugs were to see what had an effect. So they did beta blockers. Those decrease heart rate, decrease force of contraction. He did alpha receptor blockers. That's going to be a vasodilator. It's going to prevent constriction. Hopefully that would bring the blood pressure down. Third thing they did was a calcium channel blocker. That's going to block those L-type calcium channels. What does that do? Less constriction of the blood vessels. Hopefully, once again, to bring the BP down. They gave them diuretics like thiazide or furosemide, and what are those going to do? End result is hopefully not get more reabsorption of a lot of those solutes, therefore water doesn't go with it, and therefore you excrete it. And they gave an ACE inhibitor, which would do what? Angiotensin 1 can become angiotensin 2, and therefore then the blood pressure should hopefully go down. So they gave all these things, and they were still having issues, and they didn't understand why that was occurring, so they had to go in and figure out, well, what actually was going on in terms of what was causing this hypertension. And here's what they found out. Initially, this patient, one of their kidneys had stenosis, as in the artery leading to that kidney got narrowed. It was a narrow artery. So that kidney, say it's my kidney over here, this kidney is receiving less blood flow. Why? Because of the stenosis. So less blood's coming in. What does that kidney experience? What does it think is going on? It thinks, oh shit, I have way less blood pressure in here. Less blood flow is actually getting to the kidney. So that kidney makes renin. So my stenotic kidney makes renin because what's it trying to do? Increase BP. Why? Because it's sensing there's low blood pressure. Why? Because there's low blood flow. There's only low blood flow because I have the narrowing, but doesn't realize that. So I have a bad kidney and my good kidney. My good kidney is fine. He's chilling. He's got blood coming in perfectly. The bad kidney is narrowed, the narrowed arteries, so it secretes renin. Does renin affect only one kidney or does it affect everything? Renin affects everything. So in result, the one kidney increased RAS. What does RAS do for the whole system? Increase blood pressure. So what does that do? Now this kidney, the bad kidney, is happier because now it's getting more blood through the narrowed artery. So it's still not great, but it's doing better. My good kidney is now very, very sad. Why? Because now it's getting way too much blood pressure. It can't, though, bring the blood BP down. Why? Because this kidney is constantly making RAS because it's thinking the BP is too low. So there's constant RAS going on. So the good kidney, in order for it to prevent this increased blood flow in, it actually has to basically increase resistance there. So the good kidney actually either gets a narrowed artery or basically in a way tries to increase resistance. So it makes this like more vessels here or more like cells around the vessel to prevent the increased blood pressure in there. So now at the end result, before we give them any drugs, they've got a bad kidney that has stenosis that caused all this RAS, and it's constantly causing RAS to maintain the blood flow through there. And my good kidney, that's now also bad because it's permanently changed itself to make sure there's increased resistance there to fight that blood pressure. So what happens then when at that point you gave them a drug to bring down the BP? You give them the drug and both their kidneys die or they start to fail. Why? Because I have stenosis in the one and it's not going to do anything. And I have a stenosis that the body made itself to try to prevent the overall natural high blood pressure all the time. So then what happens? They go into kidney failure. And then they die in the kidney transplant. This is why a lot of these diseases, what we always talk about, preventative care, right? The idea that you want to, if you can find hypertension early, I want to bring it down early. Because what happens if I found that early enough? What would they do? I can go in and I can basically, like the cool video game stuff, where they like bring in the little stuff and they like push out the blockage, or they can make a different way to get blood into the kidney. If I can circumvent the stenosis in the bad kidney, the good kidney will stay fine, so will the bad one. The bad one then will get normal amount of blood, it doesn't make RAS, and I don't have hypertension. So that's only if they found it early enough. If they find it way at the end, well, they can still do that. They have to do now for both sides because both kidneys are now screwed up. So it all depends on not just what to give them at what point, but timing is also very, very important. So trying to find it early enough is really good. But that's what can happen if you have one stenotic kidney and you don't treat it. At the end of the day, both kidneys will eventually have issues because the RAS from the one is affecting the entire system. So you can sort of keep that in mind. Another spider thing. So once again here, we're looking at BP. Oh, this is the same one as before. So that one there. Second, another thing, we talked about prostaglandins once before on the lecture 2 or 3. Prostaglandins, like I said, they are a fail-safe for the kidney. Kidney, after the brain and the heart, kidneys always need some level of blood flow. If they get no blood flow, the kidneys die. So you must have blood flow somewhat to the kidneys. So if you go into fight or flight, does my body want blood going to the kidneys? No. I'm not trying to get blood into to filter stuff. When you see something you're freaking out and you start running, the kidneys' arteries close up entirely. You maintain that, your kidneys die. Kidneys go, oh shit, what do? They release prostaglandins. Prostaglandins are vasodilators. So the prostaglandin, you guys, someone close the door for me all the way. Thank you. The prostaglandins dilate a little bit, and that ensures some blood flow gets to them. So the kidneys stay happy and they don't die. That's what we see here, is that if you have a hypervasoconstriction and a decrease in blood flow, renal prostaglandins are released to cause dilation to ensure that we get some blood flow to the kidneys. If you look here, what do you see? Gave them angiotensin 2, that causes the constriction. However, we still get a decent amount of blood flow there. Eventually, why? Because prostaglandins were released. And they are a fail-safe for the kidney. This goes back to the lipid guy from Biochem. But remember how we talk about prostaglandins, and basically they come from phospholipid membranes, and then you have PLA2, that makes the arachidonic acid, and then all these are different kinds of different things that do different stuff. For our main purposes, our big prostaglandins, at least for what we talk about in terms of the kidneys, are derived from this tree right here, and so they use the COX-2 as the enzyme to produce those prostaglandins. Vioxx is this drug. Vioxx is a drug, it's a COX-2 inhibitor. So it prevents us from secreting or creating the prostaglandins that the kidney releases. So if you give someone Vioxx, it is a very potent nephrotoxic agent, as in it prevents the kidneys from making prostaglandins. So whenever you experience a sympathetic innervation throughout your body, your kidneys start to die because you don't release your failsafe. So keep in mind that drug and what its negative effects are. So yeah, water, intake, output. Remember, when we talk about in the GI tract, we're constantly secreting things. Saliva, different fluids, acids, all those things have water to them. And where did that water come from? It came from our ECF. However, keep in mind, when we get to the small intestine, large intestine, a lot of that is reabsorbed. So we don't always have a net huge loss. We secrete it, but we reabsorb a lot of it. But even after that, we still do get a loss of water every day. That's why we have to always make sure we have intake of water to match the output. So just keep that in mind. In general, stuff's really, really basic. So how do we control the amount of water intake? As in, how do I get more water into my system? It's all through thirst. So by making, in our brain, by making us feel thirsty, we end up drinking water to increase our input. And what will cause us to be thirsty? And this should just be pretty basic. But if we are having a high osmolarity, as in there's too much salt in there, we want to bring in water. Why? To then make sure to bring the osmolarity down. Or if my blood pressure or volume goes down, what does that mean? I've got less volume in my blood. How do I want to bring more blood in? Well, I could definitely do reabsorption. But aside from that, I want to increase my input. So you can increase your input by the thirst sort of pathway to ensure that, okay, I'm bringing more water in initially into the whole system. And lastly, angiotensin 2. Like I said before, angiotensin 2, one of the 5 things it does is it directly causes an increase in thirst in our brain so that we input more water or bring in more water. Output, same actual things as before. So how do I control the output? Well, if I have really high osmolarity, do I want to have more water getting excreted? No. So therefore, what do we have? We have something like ADH that's going to do what? Cause more reabsorption. Or if the pressures go down, volumes go down, I want to maintain more water, I keep it in. Angiotensin 2, same idea. These three, trauma, surgery, and drugs, we're not entirely sure what the mechanism is. We know that when you have these, you get more ADH and more water reabsorption, but we don't know exactly how those things mechanistically cause that. And this is the whole thing together. If you have too salty or not enough pressure, not enough volume, you have more thirst, more ADH, those can cause more water to get reabsorbed, we retain more of the water. Or we have more water put into our system as we drink it, stuff like that. Sodium levels. So basically, if your sodium levels go up in terms of our diet, it takes about a day or two for us to see the effects of that. So if I had a high sodium level, I had like Bitmax morning, lunch, and dinner, and then we would actually see an increase in excretion for like a day or two. So it's not an immediate change. It takes some time for the hormone levels to change to end up us getting the exchange in excretion. That's why the intake occurs, and it basically a day or two we see the change in terms of the actual outtake, the excretion. Also keep in mind, sodium levels are very similar to your body weight. Why is that? What follows sodium? Water. So if you have a lot more sodium intake, which means that I reabsorb more sodium, water is going to be following that as well, and that's why water. A lot of how much of our body is water? What's TBW? 60%, right? 60%. Is it 60%? Yeah, 60% of a 70 kilogram whatever person for TBW. Don't forget all those terms from the first lecture. They are going to be on the exam. So the water, our overall body weight is going to, in a lot of ways, mimic our sodium levels because water follows the sodium, and therefore is going to be one of the main contributing factors to our overall body weight. So yeah, we got this one here. So if sodium goes up, and once again, we already know all of this. So we'll just talk through it. We'll go through it real quick. If I have a lot more sodium intake, what's going to follow the sodium? The water. Therefore, the blood volume goes up. So first things first, if my volume goes up, what happened to my plasma protein levels? What is plasma protein? It's concentration. Shit over water. I've got way more water, same amount of plasma proteins. Overall, the osmolarity went down. And osmolarity is part of GFR. That's why I want you guys to think about it in terms of osmolarity, because if this osmolarity is less, GFR goes up. GFR goes up, which means what's going to happen then? More stuff's filtered, more sodium excretion. So that's the middle part. Volume goes up, obviously the pressure goes up. If our pressure goes up, what is going to be the para or simple response? Less sympathetic. Less sympathetic, and that all feeds into the JG cells, so they make less renin. So all of RAS goes down. Less RAS goes down means there's less reabsorption, therefore more sodium is going to be excreted. Aside from that, if the blood volume goes up, what's going to experience that? The atria. The atria are going to see high pressure, high volume. They release ANP. ANP acts as a dilator and also causes more sodium excretion. So that's how it's all related. So it all kind of comes together like that for what we've already been talking about. If I go to this one. What the hell? Okay, so. And then hemorrhaging is basically the opposite. Hemorrhaging, what happens? Well, we lose blood, right? So we've lost our blood, our volume goes way down. Our volume is down. Did the atria release ANP? No. Atria are since, we're good. We don't have stretching too much. We're not good. We don't have any blood. But the ANP is not released, so therefore there's not going to be any excretion, or there's going to be less of it. Aside from that, if the volume goes down, your pressure goes down, obviously your sympathetics increases, all of RAS gets activated. That's why all of the RAS will increase. What do those cause? Less excretion. They cause reabsorption, right? Therefore, less excretion. Why the GFR goes down? Why does the GFR go down? Because that first value, the hydrostatic pressure, dropped. Because now there's less volume in our system. The blood can't push. There's less volume in the box. The heart can't push it through. Nearly as well. GFR decreased. So there's less overall excretion from that as well. All these things are going to cause, and also if the pressure goes down, ADH is going to increase to get more reabsorption of the water, less of it getting excreted. And that result is going to be to try to bring our blood volume, our blood pressures back up. This I already talked about at the end of lecture 1. So I'm not going to go over it again, but you need to be comfortable. I'll go over these last years, that's what we're talking about today. But you need to know which of these is a volume contraction or an expansion. Like I said before, the defining characteristic is the ECF. If the ECF shrinks, it's a volume contraction, regardless of what the ICF does, always. Same thing with an expansion. If it's a volume expansion, it's the ECF expanding. Even if the ICF is getting smaller, it still counts as an overall volume expansion because it's only in reference to the ECF. We've talked about these already before. These last two are are important to what we talked about today. Adrenal insufficiency. What happens with adrenal insufficiency? I don't make aldosterone, right? I have less aldosterone, which means what happens to my sodium? Do I reabsorb it? Nope, you're right. I lose it. So sodium goes down. My sodium levels decrease. Therefore, I'm losing salts overall. Osmolarity decrease. For all these, you need to know, does the osmolarity go up or down? And what happens to each compartment? But in this case, no NaCl reabsorbed or less sodium reabsorbed. I lose osmolarity. So my osmolarity went down. Why does my ECF shrink, first of all? Why does my ECF get smaller? Water goes with it. Right, water goes with the sodium to some extent. But then on the next part of the question is, why does the ICF get bigger?
Because potassium gets back.
Yeah, so what we see, well, so for the ICF, not really from that, you're on the right idea, but what's happening here, sodium is leaving, and it's going to stay in the tubule. So let me take a step back. Why is it in the beginning, why is there more volume in the ICF than the ECF up here? Why is this bigger than that? Why is this 28 and this 14? Why is there more water in the ICF than the ECF at rest? What causes water to be anywhere? Salts. So which of those has more salt in it? ICF. ICF has way more potassium salts than is in the ECF, sodium salts. That's why there's 28 liters of water here, only 14 here. So when we go down here, I'm losing my sodium, total sodium amounts from the ECF. Am I losing any potassium from the ICF? ICF potassium is staying the same. So let's just say I had 10,000 potassium here and like 4,000 sodium here. Then 4,000 sodium becomes 2,000 sodium. My potassium is still the same. So some of this water does get excreted in the urine, but a lot of that water that was in the ECF, guess where it goes? To the ICF. Because effectively there's more salt now in the ICF than when we were at rest. So the ICF expands because some of the water that was here moves this way due to osmosis. Because I lost sodium, some of that water then falls to sodium, but a lot of that water actually moves into the ICF. That's why we get a slight expansion of the ICF, even though the ECF is getting smaller from that there. Volume expansions, where the ECF gets bigger, SIADH, syndrome of inappropriate ADH, as in you're making way too much ADH, way too much vasopressin. So therefore, then what's going to always be happening? Water is going to be reabsorbed, even when we don't want it to be. And that water goes to which compartment? Both, because water is going to go wherever there's salt. So water definitely goes to the ICF, and it goes to the ECF. Why does more water go to the ICF? Because the ICF has overall more salts than the ECF does. And that just brings the osmolarity down. All right, last thing here, congestive heart failure. Big takeaway from this is a cycle. As soon as you get this, all this bad shit happens, and that makes this even worse. And then the bad shit keeps going, and then eventually you die. Okay? So, unless we can try to treat it. But this is why once again, the big thing is preventative care, right? When everyone's applying to medical school, make sure you talk about preventative care in all your applications, because every med school says, oh my God, they know preventative care. But that's the whole idea, is that like something like this, we can still treat you if you have heart failure, but if we can prevent the heart failure from occurring in the first place, I don't have to worry about all of this bad stuff going on top of all the other bad stuff that caused that in the first place. So preventative care is key. But if you have heart damage, some sort of heart failure, what's going to happen? Well, your heart isn't working properly. Your heart's not working properly, you get tachycardia, the ventricular dilation, your heart cells are getting bigger and bigger, and they work until they can't get any bigger and they can't be as functional. You have a decreased cardiac output, as in your heart isn't pumping as well as it needs to. If I have a decreased cardiac output, I've got less blood going to the kidneys overall. Less blood's even reaching the kidneys. Kidneys aren't being perfused as much as we need it to. Therefore, if they're not getting perfused enough, less sodium, in terms of this going here, less of it's going to be perfused. You're going to have issues with your sodium retention. From that, you get an increase in the osmotic pressure. But the big thing here overall is be aware of the ADH. As in, you're going to have your overall increase in ADH because of all these other issues, what does ADH mean that we're doing? We're maintaining our water. As in, we have way more volume in our system. Is that good or bad for the heart? The heart already isn't working properly with a set volume. Because it's not working properly, I end up overall making sure I absorb even more water. So now the heart was already shitty, and now it's dealing with even bigger volumes. So it actually feeds back, and it makes the heart even worse. And it actually damages the heart even more, which means what happens then? Less output. This is a cycle. It gets worse. It's a preventative degeneration. It gets worse and worse and worse. One key thing here is the aquaretics. Aquaretics, the one good thing with them is that they're going to prevent the ADH. They're going to screw up the ADH and ensure that we don't reabsorb the water. What they found is that aquaretics do not increase their survivability. They still die at the same rate, but they feel a lot better. As in, like, there's a lot of like palliative care in terms of giving the aquaretics. It'll make them, they physically feel better. However, we haven't seen any statistical increase in life expectancy once this has already occurred. Because keep in mind, it's a cycle. The biggest things I would keep in mind, once again, is the heart damage causes cardiac output. Some mixture of things going on in here that screws up the perfusion of the kidneys. End result is we get more ADH, to get more reabsorption, to make bigger volumes that end up hurting the heart even more. And it keeps going like that. Aquaretics can be used here, but more in terms of like palliative care, less in terms of having an overall, like trying to solve the problem. A lot of times when you have like especially massive heart failure, you can't really solve the problem unless you give them a heart transplant. That's usually like the go-to for that stuff there. What's up?
So in between decreased renal perfusion and increased sodium retention, what can we say about filtration fraction?
Yeah, that's something, because when I look at this, like when I think of if there's less perfusion of the kidneys, then, oh yeah, so because there's less perfusion of the kidneys, basically there's less filtration going on. So less sodium is getting filtered out. So more of it just stays in the blood.
So would our filtration fraction still like be at 20%?
I mean, assuming that there's less blood flow to their overall, both RPF and GFR would go down. Both things would go down, but overall, there's less total blood going to that area, so there's overall less sodium is getting filtered out. So that's why we retain more of that. And that retention of the sodium is what's going to lead to our overall, we want to eventually get more ADH so that we can actually reabsorb even more of the water that was in there to begin with. Okay. Nice. Is everyone good?